Welcome, students. We continue our discussion on section 2.4 on conditional probabilities. In this particular video, we'll study a new theorem that apply on partitioned sample spaces. Let's start by defining partitioned sample space. A set of events A1 through AN, partitioned sample space S, in a case when union of those AIs, so union of A1, A2, and so on up to AN, makes up the whole sample space S, and AIs are mutually exclusive. In other words, intersection of AI with AJ is an empty set when I is not equal to J. And the following theorem, theorem 2.4.1, gives us an opportunity to calculate unconditional probability of event B that is defined on partitioned sample space S. Now, let's prove that theorem. So we have AIs. This is a set of events that is defined the following way. Union of them is the whole sample space. They are mutually exclusive. Then for any event B, we can calculate it using the following conditional probability of B given A. Now, let's take a look at the following sample space S and our event B. Now, you can see that event B can be merged from its intersection with those partitions AIs. So B can be merged from the following pieces. Which are intersections of B with those AIs. In other words, B might be expressed as the following union. Union of intersection of B with A1. Let's say this yellow part here is A1. Union with B intersection A2. Let's say that green part here is A2, and so on. Up to AN. If B doesn't intersect with one of these partitions, then it is okay, since it's going to be simply an empty set. Now, all these events inside of these brackets here are mutually exclusive, since AIs are mutually exclusive, meaning we can express probability of B as the following sum. Probability B intersection with A1, probability B intersection with A2, and so on. Now let's recall our formula for conditional probability. Probability B given A is equal to probability of B intersection with A over probability of A, from which we can express probability of B intersection with A as probability of B given A multiplied by probability of A. Now let's come back to our equation here. Probability of B is then equal to probability of B given A1 multiplied by probability of A1 plus probability of B given A2 multiplied by probability of A2, and so on, up to probability of B given AN multiplied by probability of AN, which concludes our proof. Now let's take a look at a couple of examples. So we have urn1. So this is a bucket which contains 2 red and 4 white chips. So I will color the red chips in black and 4 white chips. We have urn number 2. There are 3 red and 1 white chip. A chip is drawn from urn 1 at random and transferred to urn number 2. Then a chip is drawn from urn number 2. Here is our urn number 1, urn number 2. What is the probability that the chip drawn from urn number 2 is red? So probability that we get red chip on our second draw from urn number 2. Using our freshly studied theorem here, we can express unconditional probability of red chip on second draw as probability of red on second draw, given that we got red on first draw multiplied by probability of red on a first draw. By first draw, I mean a draw where we transfer a chip from urn number 1 to urn number 2. And by second draw, we mean our draw from urn number 2 plus probability of red on the second draw given that we transferred white chip. So white chip on the first draw multiplied by probability of white chip on the first draw. Okay, this is true since the events red chip on the first draw and white chip on the first draw, these two, they partition our sample space since there are no other options. Either we transfer a red chip from urn number 1 to urn number 2, or we transfer a white chip from urn number 1 to urn number 2. Okay, now let's calculate these probabilities. What is the probability that we draw a red chip on our second draw? What's the probability we draw a red chip from urn number 2? Given that a red chip was transferred. If we transfer a red chip on our first draw, then there are going to be 4 red chips and 1 white. So this probability is equal to 4 over 5. Multiplied by probability of a red chip drawn from a first turn. So there are 2 red and 4 white, meaning that this probability is equal to 2 over 6 plus probability of drawing a red chip from a second turn, given that we have transferred a white chip. If we transfer a white chip on our first draw, then there are going to be 3 red and 2 white chips. So this probability here is equal to 3 over 5 multiplied by probability of transferring a white chip. There are 4 white and 2 red, meaning that this probability is equal to 4 over 6, which is equal to 2 over 3. Okay, now let's take a look at one more example. Three chips are placed in an urn. One is red on both sides. So first chip is red on both sides. A second is blue on both sides. And a third one is red on one and blue on the other. So blue on one and red on the other. One chip is selected at random and placed on a table. So we draw one chip at random and place it on a table. Suppose that the color showing on the top is red. So the color showing on the top is red. What is the probability that the color underneath is also red? Thus, we are looking for probability that bottom color is red, given that the color on top is red, which might be expressed as probability that bottom color is red, intersection with top color being red, divided by probability that the top color is red. Now, probability that bottom color is red, intersection with top color is red, it means that we have drawn a chip that is red on both sides. And there is only a single chip in our urn, which has both red colors. So this probability here is equal to 1/3. Now, a probability that the top color is red. There are three events that partition our sample space in that case. Either red-red chip was drawn, blue-blue chip is drawn, or red-blue chip is drawn. So probability that top color is red given that red-red chip is drawn, multiplied by probability of red-red chip being drawn, plus probability that the top color is red given that red-blue chip is drawn, multiplied by probability of red-blue chip, plus probability that the top color is red given that blue-blue chip is drawn, multiplied by probability of blue-blue. Now, probability that the top is red given that red-red chip is drawn is equal to 1. Since both sides of that chip are going to be red, meaning that the top will automatically be red. Multiplied by probability of drawing red-red chip is 1/3, plus a probability that the top color is red given that red-blue chip is drawn is equal to 1/2. Multiplied by probability of red-blue chip being drawn is 1/3. Plus, what is the probability that the top color will be red given that blue-blue chip is drawn? It is equal to 0, multiplied by probability of blue-blue chip being drawn, which is 1/3. Okay, so we have 2/6. So that will be 6. This is 2/3 then.